So we'll be adding breakpoints in this video, and breakpoints are basically of two kinds: software and hardware. Hardware breakpoints are traps that are set on the registers, the debug registers, that is, and so their number is going to be limited, obviously bottlenecked by the number of debug registers that you have in your system. Software breakpoints, on the other hand, change the machine code that has already been compiled and is being run. So when you set a software breakpoint, it actually updates the underlying compiled binary that you are debugging. You can have unlimited number of software breakpoints because you are replacing underlying uh, machine code. So you can have as many breakpoints as you want, well, bottlenecked by the number of bytes there are in your compiled binary. And a single line of source code, the code that you write in C++ or C or something, uh, therefore a single line of that code can have multiple breakpoints because a single line is compiled down. When it's compiled down, it has multiple bytes. Basically, each line is multiple bytes long, and you can set a breakpoint on each of those bytes. Basically, on those instructions, you can replace the instruction out. And therefore, a single line of code can have multiple underlying instructions, and therefore you can set multiple breakpoints in a single line. So hardware breakpoints, they work by trapping execution when a given address that is stored in a debug register is executed or written to or read from. So you basically store addresses in the debug register, and when the code at that address executes, or the memory at that address is accessed, the hardware breakpoint is trapped. Basically, the hardware breakpoint is triggered, while the software breakpoints, they happen only on execution. We can also set breakpoints on the go. You don't need to set the breakpoint and then compile. When your code is being run, you can actually set breakpoints in the middle of it, right? So that means that we are going to be changing the underlying machine code on the fly, because we are setting the breakpoints on the fly. And the debugger needs a way to tell when the control has reached a breakpoint. So this changing of memory that I'm saying, that we're going to change the underlying machine code itself. The machine code is loaded into RAM. This changing of memory, the machine code in the RAM, can be done using a ptrace command, a variant of the ptrace command, which we will see very soon in action. But what do we change the machine code to? And what will pause the execution when we change the machine code and let the debugger know that a breakpoint has happened? Let me bring up a small diagram for you guys. So what we need to do here, we have a debugger and we have a debuggy process. So the the code is being executed in a debuggy, and we want instruction 3 to have a debug point, breakpoint after it. This point in red, we want that. But what do we need? How do we insert this breakpoint? What do we change in the underlying machine code? And what is this mechanism? We have this arrow that is taking the control back to the debugger, but how does that actually happen? What is the underlying mechanism? So we will explore all that in this video. So this red arrow, what this red arrow implies is that we are inserting an instruction in the debuggy machine code, right? So this work of this red arrow is to insert that instruction into the machine code, and this is what the ptrace command will do. But what do we need to insert? What type of instruction will pause the execution of the debuggy and tell my debugger to come alive? So the answer to that is the int3 instruction. So int3 is a special machine code. It's a special instruction. And when the control comes to this instruction, the CPU doesn't know what to do with it. And so it sends an interrupt to the OS. On Linux, we have an interrupt vector table, and that is used to configure handlers for different interrupts. So int3 is a special instruction. It will send a special kind of interrupt, and the Linux interrupt handler table already has this handler defined in it, that when you encounter an int3, you send a sigtrap signal. All right. So for the int3 instruction, it looks up and executes the breakpoint handler. The OS uses a sigtrap signal to halt the execution of the debuggy. The OS will send a sigtrap to this debuggy. The sigtrap signal is like the sigkill signal which we used in one of the previous videos to kill the process. It stops the execution of the debuggy. The process basically, it will stop the execution of any process that received it from the OS. In our case, that's going to be the debuggy. And so when our debuggy receives a sigtrap, it will update the state of the debuggy, and we are already hearing and listening to that change of state in the wait pid syscall. We are using a wait pid syscall to listen for any changes to the state of the process. All right. So when our process will receive this uh, sigtrap, it will update its state, and we have a wait pid going on right here that is listening to this change of state, right? So that's how this execution will, this debugger will come alive. It is listening to that state change on that sigtrap signal that is being sent by the OS when the CPU encounters an int3 instruction here. So what happens is we insert an int3, the CPU executes them, CPU sees int3, it goes to the OS. OS says, oh wait, this is int3, we need to send a sigtrap. It sends a sigtrap to debuggy, that changes the state of the debuggy, and we are listening to that change of state in our debugger using the waitpid syscall, and that will bring my debugger alive. That's basically the mechanism of how breakpoints work. Software breakpoints. Our function right now, it's just listening for OK and error. We need to specifically listen for the sigtrap variant in OK. If you were to open the code and go to main, you see we have wait status stopped. Similarly, there is going to be something as wait status sigtrap, and we need to be listening to that. Where do we need to do that is wait on right here, wait on signal. You see right here, we're just checking that waitpid didn't throw an error. But instead of that, we also need to check what type of signal or what type of change happened to the underlying process. So right here, like in main, we are listening for specifically stopped, and then all the other cases go into this okay. We need to listen for the sigtrap signal and handle the underlying debuggy process right there. When this happens, we can see what line should be executed after the trigger by reading the rip register. So when the CPU executes these instructions, it maintains a pointer. So when the pointer is here, the CPU will run this instruction and then move the pointer one ahead. Then it will move one ahead. Then it will, when the pointer will be here, the CPU will execute this instruction, see that it is an int3, update the rip register, and signal the OS. All right. So by the time the OS is signaled, the rip register has already moved 1 byte ahead. So int3 instruction is just 1 byte large. And by the time the OS signals our debuggy with the sigtrap, the rip register has already moved on beyond the int3 instruction that we inserted right here. All right. We need to keep that in mind. That will be important later on. So the rip register will tell us on what line of code basically we were when the debugger came alive. The rip register will be pointing to the address following immediately after the line that caused the debugger to come alive. Right now we are dealing with software breakpoints, and when you run any program, each instruction in the machine code has an associated virtual memory address. So right now you only see instruction 1, instruction 2, instruction 3, but actually each instruction has a virtual memory address associated with it. It looks something like this in your memory, and at that note I would highly recommend watching a video. The video is how CPUs run functions. It's going to be this video. So I highly recommend watching this how CPUs run function by core dumped. It's an excellent video. and I do recommend watching it before coding along with me. It's just 19 minutes, so I'll trust you do that. We want to set breakpoints at certain memory addresses. So these software breakpoints are actually set on these memory addresses, and that video will explain to you how these memory addresses actually work on the CPU. And I can try to explain it, but he explains it better than me. So why not let him watch his video? We'll set these breakpoints on these virtual memory addresses. Uh, and so we will create a struct that will represent a software breakpoint for us. We need that. We need a struct basically that will represent a software breakpoint, and it will store inside it the virtual memory address at which the breakpoint was set. So let us do that. So what I'll do is let's go to source cd rdb, and I will create a directory. I'll call it, what should we call it? We'll call it stop points. All right. Cd into stop points, and in here create a file called breakpoint.rs. All right. And I will write it and I will quit, because I also need to create the mod.rs. And pub mod breakpoint, write it. The file is not included anywhere in the module tree. The Rust analyzer cannot offer IDE services if you are in, what's wrong? And then breakpoint.rs. So we have a mod outside, right? ls nvim mod.rs. We also need to define the module here as well. So the module is going to be pub mod. It was stop points, right? Stop points, write it, quit, and now cd outside nvim. So in the RDB you're going to have breakpoints. All right, so right here we want to create a struct, pub struct, let's call it breakpoint, and it's a breakpoint on virtual addresses, not the debugger breakpoint. So we'll call it breakpoint va for virtual address. So our program can have multiple breakpoints, so each breakpoint should have an ID so we can identify them. So let's just usize for it, and it's going to have a virtual address, and we will use the virtual address struct that we created in one of the previous videos. The previous video basically, right here, we will import it and use it. And each breakpoint may be enabled and disabled. So we'll keep a flag telling us whether the current breakpoint is enabled or not. So is enabled, and let's call its data type will be Boolean. And we will also keep, okay, so the diagram that I showed you right here, we are actually inserting, but instead of inserting, what we will do is we will replace instruction. So if you want to set a breakpoint at instruction 3, we will replace the instruction 3 with the int3 instruction. So this instruction 3 will be replaced by this special instruction. So the instruction that we are replacing, it needs to be stored so that it can be restored again. So what we'll do is we will create an instruction replaced here, and this will store whatever instruction we replaced. And since int3 is just 1 byte, so we will store the 1 byte that we replaced. Our program is going to have multiple breakpoints. Never used. So our program is going to have multiple breakpoints, and to keep track of all those breakpoints may become tedious. So what we'll do is we will create a wrapper collection around it. We'll create a collection of breakpoints in the process struct. So the process struct will store a breakpoint collection. So you can maybe keep a list of breakpoints, but I also want some helper methods around that list, so you can write those functions in the impl of process, but I don't like that. Separation of concerns is not there. So what we'll do is we'll create another struct, and that will basically be a stop point collection, and we will add that stop point collection into the process, and we will implement all those helper methods for that stop point collection. All right, we will need them for stuff like getting them by id, getting them by address, enable, disable, stuff like that. Enable by id, enable by address, stuff like that. Let's write and quit, and cdr oops cd source slash rdb slash stop points. In here I will create uh let's call it stop point collection, step stop point collection rs, and let's write it for now. Write an empty file, quit it, uh, ls nvmod.rs pub mod stop point collection, write quit cd cd ls minus let's create the struct pub struct stop point, and it's going to be a generic. Right now we only have software breakpoints, but the same collection can be then used for hardware breakpoints. Stop points is going to be a vec of s. All right, but we need to somehow constrain this s. It can't be anything, right? It cannot be a string or an int. It has to be a breakpoint. So let's define a contract, a trait for a stop point. So stop point, and in this stop point we'll have a getter for its id. It takes a self and it returns a usize. We need a getter for address. So and the address is going to be a reference to the virtual address stored. Virtual address. Then we need another function to tell us if the breakpoint is enabled or not. So is enabled, and it's going to return a boolean. Then we need two functions to enable and disable the stop point. So let's make it enable, and instead of usize, it's going to return a result string in case of error, and it's also going to take the PID. We need that because we need the PID to do the syscall. We need the process ID for the syscall that will be used to enable or disable a breakpoint. So I PID unisted, and similarly we're going to take a PID in disable as well. and similarly it's going to return a result of nothing in case of success and string in case of error. That's the trait, and we need to constraint it right here. So the S must implement this stop point. And since we want to store breakpoints in it, we need to implement this trait in breakpoint. But before doing that, let's implement the helper functions I told you about. We will implement them right here. Impl. So it will be implemented for any type that implements stop point collection, and it takes that S. So we need a function to push a new breakpoint into the vector. So pub fn push, and it's going to be mutable because we are pushing, so we are updating stop point, and it's going to be of type S, and we'll return a reference to that, a mutable reference to the breakpoint. So self dot stop points dot push, and we will push the stop point, and then we need to return a mutable reference, right? So stop points dot last mute, and we will unwrap it because it returns a result. That's it. Then we need a function to check if an ID exists in that stop point vector. So pub fn contains ID, and of course it's going to take a self and an ID, and for us the ID is usize, and we will return a bool. So self dot stop points, we will iterate over it, and then we will check if any breakpoint, so any stop point has that ID or not. Sp dot ID, the getter, equals to the ID, and this will return a boolean, and we'll return that boolean. Okay, then we need something similar for address as well. So let me copy 3 lines and paste them, and contains address, and instead of ID it will be a reference to a virtual address, and let's call it address, and it will return a boolean, and instead of checking the ID we need to check the address, and it needs to be equal to address, and this equal to should work, because if you see we derive EQ, and when we derive the underlying uh, the fields that make up the struct will be compared. So this should work. Implicitly returns as its body. My bad, guys. No semicolon right here. Uh, After contains ID, we need a function to check if a stop point is enabled given its ID. So what we'll do is pub fn is stop point enabled by address, and it will take a reference to self and a virtual address, virtual adder, and it's going to return a boolean. Right here what we will do is we can again use an iterator here, right? So self dot my bad, self dot stop points dot iter, and in here I want to find the breakpoint by its ID. So stop point, and we want to return any whose address matches. So that will give me one breakpoint whose address matches, and to that I want to map a function, and this function, uh, what we want to do, we want to return if that stop point is enabled or not, right? So we have this. If that works, this should return a result, right? Yeah, this is enabled dot map. Let's see what it returns. What does it return? It returns an option. Okay. So in case we get an option, so we need to unwrap it. If we unwrap it and it's none, we will throw an error. So we don't want that. We want to return a false in case of none. So that should do it. And when I write it, Cargo Clippy will format it for me. I guess that's fine. And I want to get a breakpoint by its ID. So get by ID, and it's going to take a reference to self and an ID, which is going to be usize, and it's going to return an option to a reference of S. And what we'll do is, again, we will iterate and just find using the dot find method. So self dot stop points dot iter dot find p dot id, id, and that should return an option of references itself, I guess. Huh. Iterator iter macros. So it returns an option of self item. Is that right? Bro, what happened? Uh-huh. That's a macro. We're not using a macro. We're using the find function, right? I guess. Let me check. So this will return an option of a reference of S, which is exactly what we want. And I want a similar function, but by address now. So I'll copy 3 lines, paste them, and we'll get by address, and it's going to be a reference to a virtual address, and we'll return the same thing, and instead of ID we will get the address, and instead of ID here it's going to be the address. Essentially the same thing. And so this will return immutable references, but we may need to mutate the underlying breakpoint. So we'll create two functions that are basically this, but instead of immutable references, they will be returning mutable references. So I'll copy 6 lines, I'll paste them, and I'll call it get by ID mute. And instead of iter, just make it iter mute. And here as well, make it mute and make it mute and make this mute, make this mute, and hopefully it compiles. Cannot borrow self dot, so this needs to be mutable here. Then Rust analyzer is not screaming at me now, so I guess we're fine. So we're getting by address and getting by ID, mutable and immutable. The next thing we want is to remove a breakpoint from the vector given its ID. So pub fn remove by ID, and we will take a reference to self and an ID, which will be a usize. And what do we want to return here? Do we want to return a reference? We will return not just the reference, we'll return the item as is, because we have returned it, removed it from the vector, so we can remove its ownership as well by returning it from here. So what do we need to do here is we need to first find its index, and because before we remove it, when we remove it, we also want to disable it. So we need to get it from the stop point. So let's find the index first. So self dot stop points dot iter, and I will get the position of the breakpoint whose ID matches the ID given to us. ID, and that should return me an index, but it does return a result, or does it? It returns an option. So it returns an option. So I need to if let sum, if it was existing in their position, equal to this. So position should be the index. So we'll remove by index. So let mute stop point equal to self dot. In that case, I guess it needs to be mutable, na? Needs to be mutable. Stop points dot remove by the position, and before returning I need to disable it. Bp dot disable, and sum of bp, otherwise we can return a none. A local variable with the similar name exists. Oh, sp, not breakpoint. Stop point dot disable, and disable takes an argument. So to disable we need to pass in the pid, and so we will need to pass in the pid right here as well. So this function must take a pid as well. You might have meant to return this value. Yes, we did. So what I'll do is else, and remove this mutable. Why? But disable takes mutable reference, right? It must. So yeah, we made a mistake. These need to be mutable right here. Mute and mute. What else? Did I miss something? Let me just go through everything. I don't think so. If we did, I'll fix it later on. sp.disable, we're returning, but anyways, we're removing it. So that doesn't matter if it throws an error. Okay, so we have removed by ID, and let's do the same thing by address as well. So one, remove by address, and it must take address, and it's going to be a reference to virtual address, and instead of ID we will match the address. We got the position, we removed it, sp.disable. I guess that's fine. We need two more functions. One is to tell us if the vector is empty or not, and the other to return its length. So pub fn is empty self bool, and self dot stop points dot is empty, and pub fn len of self, and it's going to return a usize. Self dot stop points dot len. All right. Now we need two functions that will apply a lambda function to our collection. So I want uh, these functions to take a reference to a lambda function, iterate over all the elements in my stop collection, and apply that function. So the use case for it would be to enable and disable all the breakpoints. So we'll pass in a lambda function that will be taking a stop point and just calling the stop point dot enable or stop point dot disable function on it, so that we don't have to iterate over them. We are abstracting that iteration in this function. So what we'll do is we'll create pub fn for each, and this for each will take a reference to self, and it needs to take a lambda function. So this f must implement fn, and fn of something that takes a reference to s. All right. What we'll do is for sp in self dot stop points, we'll call f on sp. Consider borrowing here. So either you can put a reference right here, or what you can do is instead of putting there, you can put right here. So this sp will be borrowed. And then we need, so this takes a immutable reference to s, right? This function right here takes an immutable reference to s. So we want a function that takes a mutable reference as well. So we'll call it for each mute, and of course self needs to be mute here. It must take a mutable reference, but fn doesn't work. You have to use fn mute, import that as well, and this reference here needs to be mutable as well. And I guess that's it. Cannot mutate, cannot borrow f as mutable as it is not declared as mutable. Okay, so this f needs to be mutable as well. Okay, so this will iterate over the stop point and apply that function for us. The other thing we should do is probably implement the default function. So we'll impl for any struct that implements the stop point default for stop point collection that takes that s, and we will implement default, and we'll create a self object, and stop points is going to be a vec of new, basically empty vector, and that's it. You can add it dine here. Is that an error? Why is that an error? Default for stop, oh stop, not stop point, stop point collection. We don't need to box the type, and that's it. Let's see if cargo build works. All right, it does. Okay, so we'll add it to the process now. Let me just confirm that I've added them to the mod correctly. So mod breakpoint and stop point collection. All right, seems fine. And here I've added stop points. All right. Okay, so now we can add them to our process. So let's go to the struct, and in here we need to add pub stop points, and it's going to be stop point collection, and here it needs to be a breakpoint va. But this won't work. We will need to implement all the methods for breakpoint va. So yeah, it doesn't implement the trait. All right, we'll do that then. Let's go here, and we need to implement what was the trait? Stop point. The trait is not implemented, so implement stop point for breakpoint va, like so. And we need to implement all the functions, right? So let's see, where is that? Not here. Stop point collection. So we have 1 2 3 4 5 functions. id address is enabled, enable and disable. So the first three functions are quite simple. So the functions that we need to implement are id getters and id getter at the address getter, and basically the enabled getter. So fn id and self, and it returns a use size, and cell dot id will return self dot id, and similarly fn so take self, and we need to return a reference to virtual address, like so. Self dot virtual address. Then we need to implement fn is enabled. This is boolean self dot is enabled, and now we need to implement the enable and disable functions. We'll keep them empty for now. I will do that later on. Fn enable So enable takes a mutable reference to self, PID, and it returns a result, right? Result over empty and string in case of error. So for now, let's just do this. And 3 p, let's call this one disable. Uh, cannot find PID, so we need to import PID. Consider borrowing here. Okay, since it's going to be a reference. Before implementing these enable and disable functions, I want to basically just first implement the constructor for it. So I will implement breakpoint VA, and a breakpoint must not exist without a process. So what we'll do is we will create breakpoints for processes. So pub fn create for process, and we'll take a virtual address where we want the breakpoint. So process process, and the adder will be a virtual adder, and it returns a breakpoint VA. All right, so we need to return self virtual address can be adder is enabled. Let's say all are disabled at first when they're created, then we enable them. And let's say instruction replaced right now is 0 for default. Now for ID, a process may have 100 breakpoints. So the ID depends on the process. So we will get that ID from the process. Let what we'll do, we'll update it. Process dot we don't have it right now. Breakpoint ID, so it needs to be mutable here. We will increment it process dot breakpoint ID plus 1, and then we will set the ID to be process dot breakpoint ID, and we need to add this breakpoint ID to our process struct. So breakpoint ID and its usize, and we will need to add it to the constructor here as well, right? So I guess we have a new function here, new in process.rs new here, right here. We need breakpoint ID to be 0 at first, like so. We sync initializer. All right, so we also need to stop points is going to be stop point collection of default, like so. That fixes the constructor, and constructor here should work as well. Field is private, so let's make it public. What's the issue, guys? So the Rust analyzer is not screaming at me right now. I'm assuming it works fine. And I need another function that will tell me if this breakpoint is at that address. So pub fn is at, and of course it's going to take a reference of self, and it's going to take a virtual address. So virtual address, and this needs to return a bool, and what we need to check is that self dot virtual address is equal to adder or not. And now we can finally implement these enable and disable functions. Let's start with enable. Right here we will, what does it say, consider dereferencing the borrow. What the hell, where did the code go? Oh, this need to dereference the adder right here. Huh. Okay, so let's start with enable. We'll implement this enable function first. So when we put a breakpoint at a virtual address, I showed you that we are replacing that byte at that address with a special instruction, and we need to store this in instruction replaced. We can get that particular instruction using a ptrace command. So we will read that instruction using a ptrace read, and then we will update it using ptrace write. So let's just first check if this so if self dot is enabled already, then we don't do anything, right? We return an okay of this, but otherwise we will read the data at that particular virtual address. Ptrace read. So I need to import it, right? Ptrace nix ptrace. Yeah, so control N ptrace, we'll import it, read, and this, as you can see, it takes a PID and a reference. So we need to give it the PID and the virtual address as a pointer, as a mutable pointer. So we'll do that. The PID, and we need to enable, right? So self dot virtual address. So that's the virtual address struct, but we need to get the raw address, which is U64, and I need to typecast it as U size and then a mutable reference, like so. Like so. And this should return the data, but in case it may be an error, so we will map the error, and it takes a lambda function e, and I will just we need to return a string, right? So format, and I'll say couldn't read data at this because of this, and from, we couldn't read it from self dot virtual adder dot adder, and the issue is e. So this gets the data. Now this data needs to be stored in self dot instruction replaced. but we can't simply just put it, right? That is because this ptrace.read doesn't actually return a U8. Our instruction replace type is U8, but it returns an I64. So we need to get only the first 8 bytes out of it, and we can do that using bit masking. So let restored, sorry, sorry, as we need to get the last 8 bytes of it, sorry, 8 bits, the lowest 8 bits of it by bit masking. So self dot instruction replaced equal to data, and we'll bit mask it, sorry, single and with ff. Now this basically, this oxff is basically 8 bits all one. So u8, this oxff is basically equal to 1 1 2 3 4 5 6 7 8. So we're bit masking and we're getting only the first lowest 8 bits out of it. By the way, this underscore that I glanced over earlier, this basically tells the Rust compiler to dynamically understand whatever data type this read function takes, and it will automatically typecast it to that data type. That's what this function does. That's what the underscore does. And so now we have uh, stored the byte that we're going to replace. Now we want to replace it with something. So we want to replace it with the int3 instruction, and which is, so we are using I64 data type because the ptrace read returns an I64, and the ptrace write expects an I64. So that's why we basically want to the int3 instruction is basically this oxcc, all right. And since we are reading the lowest 8 bits, we are only interested in updating the lowest 8 bits, all right. So what we need to do is, whatever we read, see, we read something, so this returned an I64, but we only care about the lowest 8 bits, and we want to update the lowest 8 bits. So let's update this data. Let data with int3 be equal to, what we'll do is we'll bit mask. We care only about the leftover bits. So the first 8 bits are already taken care of. Now we want the rest of the bits. So what we can do is we can bit mask with the negation of this oxff. So data negation of oxff, this gives us all the rest of the bits, and then we will just OR it with int3, and that should create the thing that we need to write using the syscall. So ptrace of write now, write comma now, it takes the head, the adder is going to be self dot virtual address dot adder, and it's going to be as usize as mutable of whatever data type this function expects, and then we're going to write data with int3, like so. But this again might throw an error, so we will map error the error, and we'll basically use the format again. I'll say couldn't write data to this, and self dot virtual address dot adder comma e, like so. And after all of this, I can finally self dot is enabled equal to true, and then I can return an OK of OK. That should be all of it. What does it say? Self dot instruction replaced. We're bit masking it with OXFF and then we're typecasting it to U8. What's the error? I don't get it. P trace read. Let's see what the issue is. Cargo build. No implementation for result of I64 string integer. Data integer. Oh, my bad, guys. So this data is a result. We need to, oops, unwrap it as well. Huh, the error's gone. All right, so what we did was we read whatever instruction 3 was, we stored it in self dot instruction replaced. We updated this machine code and replaced this int instruction 3 with int 3 instruction, and that should trigger the sig trap which I told you about earlier. And then we set self dot enable equal to true. Now we just need to do the opposite in disable. So if not of self dot is enabled, then we return an okay of empty, nothing. But otherwise, now I need to read and restore the data that was replaced. So I can maybe copy it. Yeah. So we read data and map error, couldn't read data at, seems fine. And hmm. So this is data. This data, the lowest 8 bits of this data must be equal to the int3 instruction, and I want to replace them with whatever was stored in my self dot instruction replaced. So like similar to what we did here, int data with int3, now we will do int data restored equal to data not of OXFF, and I will OR it with self dot instruction replaced as I64, and now I need to write it using the write syscall. So let me copy the write syscall now. So we ptrace of write virtual address, and instead of data with int3, it will be data restored. Like so. Couldn't write data to this, and then self, now instead of setting it to true, I need to set self dot is enabled equal to false, and then I can return an okay of this. Let's try to build it. All right, it built fine. You know what, guys? It's getting quite tedious, so let's keep it short. And I let that's it for this video. Basically, that's what I want to say. And we will get to actually putting the uh, breakpoints and actually getting them to work in the next video. We've basically created the structures that we needed to do that. Anyways, I'll see you in the next one. Bye bye.